Hello all, my name is Armagh. I hope that this presentation finds you well. I'll be presenting one of my studies entitled The Shape and Functionalization Influence the Bioaccumulation Kinetics of Nanogold and Oreochromis Mozambicus. Nanogold comes in a variety of shapes such as rods, spheres, and stars, and are limited to a size range of 1 to 100 nanometers in diameter. Nanogold is versatile, providing purpose in the medicinal, agricultural, cosmetic, and electronic industries. The Mozambique tilapia is a freshwater fish species native to southern Africa, which is extensively used in the aquaculture industry and in the world of food can be considered a delicacy. Research on Oreochromis mozambicus is on the rise internationally, and the species is recognized as an ideal bioassay organism and is frequently used in ecological risk assessments as a bioindicator species of pollution. The present study includes the use of a conceptual absorption, digestion, metabolism, and excretion model, which serves as an illustration of the uptake sites, absorption routes, digestion, metabolism, bioaccumulation, and excretion of the gold nanomaterials in fish. The present study should provide valuable information regarding the bioaccumulation kinetics of differently shaped and functionalized nanogold in fish. This information should contribute to the understanding of nanomaterials, specifically nanogold, regarding the nanomaterials' behavior in complex biological matrices, enhancing the scientific basis of risk assessment. Due to such broad applications and unregulated usage of nanomaterials, exposure to inorganic nanomaterials, specifically nanometals, is inevitable due to unregulated and uncontrolled pollution in the form of landfills, sources of industrial effluent, various forms of wastewater effluent, and surface runoff. However, the behavior and subsequent effects of nanomaterials on a cellular, organ, whole organism, and ecosystem level is not well enough understood nor documented in order to establish whether a negative, neutral, or positive effect will occur. Due to aquatic life being subject to nanometal pollution and nanometals being causative of cellular toxicity, depending on factors, the bioaccumulation kinetics of differently shaped nanometals, in particular nanogold, as well as its respective effects require attention, especially in fish. Fish form an important part of the food web, providing a form of an ecosystem service. And due to nanometals being subject to trophic level transfer, this may lead to drastic effects on both other animalia and humans. My hypothesis is that the shape and functionality of the gold nanomaterials will influence the bioaccumulation kinetics in the tissues boxed in red on the screen, and that the gold nanomaterials will display specific affinities for different tissues. Thus, certain tissues will be more susceptible to bioaccumulation than others. The aim was to determine the bioaccumulation kinetics of the gold nanomaterials, specifically SETAC nanogold rods and citrate nanogold spheres in freshwater Oreochromis mozambicus. The objective was to determine the bioaccumulation kinetics of each gold nanomaterial by carrying out an uptake and depuration bioassay used to complete a quantitative differential tissue analysis. In the method, we characterized the nanogold, and the size and zeta potential were determined by the dynamic light scattering, and size and agglomeration patterns determined via transmission electron microscopy. The concentrations used in experimentation were based on an LC50, which was selected from a previous study completed by my colleague Dr. Water. More so, the principle of using 1/10 of the LC50 was applied as performed by other authors such as Barr. Thus, the following concentrations were used. SETAC nanogold rods at 1 microgram per liter and the citrate nanogold spheres at 1 milligram per liter. The bioassay experimental design for the exposure was as follows. The experiment consisted of 1 control group and 2 treatment groups that underwent exposure to nanogold rods and spheres respectively. The following tank setup was used. 3 tanks consisting of 2 exposure tanks labeled exposure tank 1 and 2, and the third tank labeled as the depuration tank, which contained clean isomedia. 5 fish, approximately 20 centimeters in length, were collected and placed in exposure tanks 1 and 2. The fish underwent a 48-hour exposure. Thereafter, the fish in exposure tank 1 were euthanized in accordance to South African national standards and regulations, and the fish were then dissected, whereby tissues were collected and prepped for later analysis. The fish in exposure tank 2 were placed in a depuration tank to undergo an 8-day depuration, followed by the same process. Water replacements and feeding of the depuration groups were completed every 48 hours. Daily recording of the physical chemical parameters of the tanks in use was completed to ensure stable physical chemical conditions throughout the test. Following euthanasia, dissections occurred whereby the following tissues as illustrated earlier were collected: the blood, the liver, muscle, gills, and GI tract. The tissues were then stored in an ultrafreezer at -80, thereafter freeze-dried and digested in acid using an advanced microwave digestion system. Due to the considerably lower exposure dose used in the treatment of the SETAC Nanogold rods, the tissues collected therefrom were analyzed using an inductively coupled plasma mass spectrometer, whereas the tissues harvested from the fish exposed to the citrate nanogold spheres were analyzed using an atomic absorption spectrometer. Statistical analysis was conducted on GraphPad Prism version 8, where graphical interpretation from frequency graphs was conducted. A Shapiro-Wilks test and 2A ANOVA Friedman's test was used to determine the significance, and significance was considered when the p-value was less than 0.05. The following results pertaining to the physical-chemical parameters of the media used in the exposures are presented in Table 1. The values include the standard error of each parameter noted. As one can observe, stable conditions were maintained during the exposure. Table 2 illustrates the information on the fish used in the study. This includes the number of fish, the average fork length, total length, weight, and gender ration per tank. The first step of the method was to characterize the nanogold. Herein is a transmission electron micrograph image of the SETAC nanogold rods displayed on the left-hand side in image A, and the citrate nanogold spheres on the right-hand side in image B at 1 milligram per liter molecular water. One should take note that the SETAC nanogold rods were not consistent in shape, consisting of some nanogold particles of an irregular shape. As previously mentioned, the study made use of a conceptual absorption, digestion, metabolism, and excretion model to help illustrate the biodistribution of the nanomaterials within the organism. So physiological compartmentalization of Oreochromis Mozambiquus was done, and 2 entry points were deduced, namely the gills and the mouth, and 1 biodistribution pathway, namely the circulatory system in the form of the blood, whereby the blood is carried to and from richly and poorly perfused tissues. Richly perfused tissues that were analyzed included the muscle, liver, and intestines, and the poorly perfused tissues, which were not included in the analyses, would include the urine and the feces, etc. If we have a closer look at the results and we consider the group exposed to the SETAC nanogold rods, uptake from highest to lowest in the following tissues occurred: for the GI tract, blood, liver, muscle, and the gills. If we have to look at the depuration results, the GI tract underwent an 85% reduction in the sum of ionic gold, and the blood underwent a 35% reduction, more or less, and the muscle underwent a 46% reduction, and the gills just less than 4% reduction. The liver, on the other hand, was the only other organ to have an increase in the sum of ionic gold over the time period, and this is perhaps due to the role of the organ. If we have a closer look at the group exposed to the citrate nanogold spheres, uptake occurred from highest to lowest in the muscle, GI tract, liver, gills, and blood. Interestingly enough, there was almost no gold found within the blood, both treatment groups. And if we had to look at the depuration, one defining difference was the slowed ability or reduced ability for the muscle to undergo sequestration in comparison to the previous treatment, where only 11% was reduced, and the GI tract, as with what was seen in the previous treatment, underwent a reduction of 76%. This, both due to the large reduction that occurred in both treatment groups within the GI tract, is most likely due to the metals or nanomaterials complexing with intestinal matter, becoming too large to be absorbed and later on being excreted. The liver, on the other hand, underwent a reduction. Perhaps this is due to a functional difference, with citrate being safer than SETAC, so it might have been processed relatively faster or more rapid. And the gills underwent a slowed ability or a good ability to undergo sequestration, and this might also be because of functionality. So some key common points in conclusion for both gold nanomaterials. There was uptake in all tissues, with exception to the blood, and that uptake primarily occurred in the gastrointestinal tract for both treatments, and that this may allude to effects on the intestinal epithelia over long term, or even on the intestinal microbiome. And another common point was that clearance of the gold nanomaterials occurred in all tissues. However, it was effective in some tissues and in others not so much. So that might be due to shape and functionality differences. And some key differences to take from it was the uptake of the SETAC nanogold in the blood and the absence of the citrate nanogold in the blood. This may, of course, be due to shape and functionality and particle stability, of course, amongst other things. On the other hand, another major key difference was the large uptake of citrate nanogold in the muscle, which seemingly was not irreversible, but underwent a slowed ability or reduced ability to undergo sequestration. And another defining factor was that the CTAB nanogold bioaccumulated in the liver. And this may be because of CTAB being more toxic than citrate, but also it coincides with the role of the organ, where the liver can be described as the main detoxification center. And another factor which is important to keep into consideration is that the liver hosts the mononuclear phagocytic system as well as the reticular endothelial system, which have been recognized as reservoirs for nanomaterials. In conclusion, the shape and functionality of the gold nanomaterials have an influence on the uptake, absorption, distribution, metabolism, and excretion in fish, affecting the bioaccumulation kinetics. Tissues such as the gills and GI tract serve as uptake sites and major translocation pathways, where after uptake can occur in all tissues. Certain tissues will be more susceptible to either both gold nanomaterial rod and sphere uptake and bioaccumulation therein, depending on the molecular interaction of the gold nanomaterials and the cellular components. Therefore, bioaccumulation may be irreversible or slow, and in others it may be fast. Bioaccumulation with slow clearance may result in sublethal cytotoxicity. Thank you.